Okay, let's get started. So we're continuing on our discussion for rotating magnetic fields. And if you recall from our last class, we saw how we built a machine, and we're just building half the machine, if you will. We're just building the stationary part of the machine, which has 3 windings that wrap around it. And the windings are completely independent from each other. So they are not referenced to each other in any way, shape, or form. Then what we do is we have a bunch of phases, and we can connect those in any way we want, or not phases, but windings. And we can go ahead and connect the phases to any which way we want. So if you remember from here, I have the original winding connection, which is the one on the left, and the revised connection, and it's the one on the right. And all we're doing is we're taking A and C, and we're swapping them. So when you walk up to, and literally what you do is when you walk up to a motor, you've got the 3 incoming leads for your power source. And then the motor has usually 3 wires coming out, and those are connected in delta Y, whatever they need to, but they're just literally coming out. And then you can connect it in any way you want. So we originally connected the motor as shown on the left. Now we're going to take A and C, and we're going to swap them around. Okay. Really, all we need to do is swap A and C. Why don't we need to swap A prime and C prime? Well, because normally those are all going to be connected together, right? This is a delta or a Y connected load. So if you have a load, and I'll just show that as some windings here, you have A, B, and C, and this is A prime, C prime, and B prime. So technically, you're not really swapping C and C prime and A prime around because they're connected to the same point. Now, if it was in a delta connection, you would be changing those a little bit. But the reality of it is you just have to swap any 2 leads, A to C, and that's essentially all we're doing to get this configuration over here. Everybody understand what I'm trying to do? Literally just walking up to the motor, I open up the motor junction box, take the cover off. Inside there are some terminations. Somebody's taped them up, and they're usually they're crimped together, and then they're bolted together in place. And all I'm doing is taking 2 of those connected positions, and I'm just swapping them around so that I have here what's shown on the left. Or on the right, I should say. So now when I take my fingers, remember what we did last class, fingers point in the direction of positive current, and then they rotate and wrap around the stator, and the thumb points in the direction of positive current going into that winding and what the corresponding magnetic field direction would be. Okay? So in the left-hand side, positive current going into A and returning on A prime, my thumb points in a perpendicular plane and gives me BA over here. That's what we did last class. We do the same thing for C. C points here at 90 degrees plus 30, wraps around, and then my thumb points in the direction here. So you can see that B sub C is here. Now, if we swap A and C, what happens? We swap these 2, right? The magnetic field that corresponds because of current flow through the windings that carrying phase A and phase C, those will swap from the left to right. So if you notice, this is now B sub A. This is now B sub B, B sub C, and B sub B hasn't changed. Why hasn't B sub B changed? Didn't touch it. You left it alone. So why would the resulting magnetic field change direction if you didn't touch it in the first place? So it shouldn't change at all. So I just swapped 2 windings. Now, since you're all pros at MATLAB, how do I change my file? Pardon? Say it again. What angle? BA and BC? Right here? Everybody agree or disagree? Go back to here. What has changed? Does phase A or B or C current actually change? Not at all. The phase A, B, and C current are all determined by the power supply. So why would those angles change? It's always going to be 0, 120, minus 120, regardless of how it's connected. I don't care what you do with the motor. Phase A, B, and C are dictated by the power supply. That tells, that dictates all the current going out. Okay? So those shouldn't change. The only thing that changes, as we showed it here, is the corresponding magnetic fields. BC and BA change. BA was at 0 degrees. Now it's at minus 120. BC was at minus 120. Now it's at 0. So how do I change those angles?
You change where it says BA equals IA, just change it to IC. Do it there.
I don't want to change it to be IA.
BA, do it. 0 degrees.
So what do I do?
A exponential BC exponential 0. Would be A exponential minus 110.
I got to put minus 120 there, right? I can't just call this one BC. Why not?
Because it's still IA.
It's still IA, right? So what causes BC to exist is because of the current in phase C, not in phase A. So I can't just call this B sub C because I'm still running IA through it, right? So the only thing that I can change is this. That becomes minus 120. Don't forget I need to multiply by pi over 180. And I'm good to go. BB, we already said it doesn't change. This goes to 0. Let's see. I got an extra parenthesis.
We need the parenthesis around.
I don't need that. I had it before, so.
Go to minus 120.
Yeah, let's just put the minus 120 here just in case it tries to do the negative. Okay. Now I'm going to save it. It's not what I wanted to do. I wanted it save as, but let's see, I'm going to swap this one back. Let me see if I can undo it. Okay, so save that. Now I'm going to save as before I make the change. And I'm going to call it this, but I'm going to call it spring 24. Okay. So now let's do that again. So this becomes minus 120 times pi over 180. And this one becomes 0. And I'll just keep that doesn't change anything. Okay. So this is my A and C swapped. So let's go back to my original one, which is here. And let's run it. So this is my, how many degrees of rotation for my current? Can you tell here? So one of those is the original one, and then one of those is rotated 180 degrees. If you remember, my omega sub t, we picked it as 180 here. So if we really want to see what it is, we run it over here. Now we look. And it's not rotating. Oh, I have to do it in two. No, it's okay here. Oh, this is 30, sorry. Try that again. Okay, so what we see is our reference is down here, and then we rotate that at 0 degrees. How do we know that? Because when we did it at 0 here, they were both pointing straight down, right? And then we did 30 degrees of current rotation, and then we see now we have one net magnetic field that has moved off by 30 degrees, and it's moved off in the counterclockwise direction. But you see what I'm doing there? This is what we finished up with last class. We did it at 0, and then we did it at 30, and we see that we started here, and then we rotated 30 degrees in the counterclockwise direction. That was what we had for our original circuit. Let's go back and open up this one, and we're going to start with 0 here. Okay, so this is the revised one. This is when we swapped A and C. Let's take a look. I guess let me see if I can try it again. Oh, I got to do it in 2 spots. That's why. Minus 120 times pi over 180 and 0. Try that again. Okay, so both start here. So you'll notice that they're not starting at minus 90 degrees or positive 270. But do I really care that they're not starting at the same one? I don't, because this just rotates around forever, right? It rotates around at whatever speed we need it to speed or operate on. So who cares if it starts over here or over here? As long as it continues to rotate, and we said it rotated in the counterclockwise direction, I don't necessarily care. And as long as the degrees is the same, if I go current degrees of 30 degrees here, I should get 30 degrees over here. So let's try that. Oh, there's a problem. Or is there a problem? It did rotate 30 degrees, but is it still counterclockwise? It is clockwise, isn't it? Is that a good thing or a bad thing? Thumbs up. Why is that a good thing?
You're changing your field to be like A, B, C, A, B, C go in the opposite direction. So you think that it would start to.
I'm not really changing the field, I'm changing the current, which just happens to change how the vectors get produced.
Right.
And then how they add up is resulting in a magnetic field that goes in the opposite direction. So is that a good thing? Change the direction of the motor, is that a good thing? It's useful, or is that a good thing?
Means you can run your motor whichever way you want. Yeah. Right?
Garrett, do you have anything to add? Yeah. Is anybody here a mind reader and know which way you want the pump to run? Clockwise or counterclockwise? You have no idea. You're just building a motor. So you can't tell if it needs to rotate counterclockwise or clockwise. How about if you're in an elevator? You can go up, but don't you want to be able to go down too? How do you get to go down? You think people flip the motor around and go from one side of the shaft to the other? No, they literally just swap the wires. So this is a really good thing. This is a great thing, because that means I can make one motor, 100 horsepower motor, and I can get it to rotate any way I want. You just have to go and change the field, or change the windings in the field, or not change the windings, change the connections in the field. And so that's literally what you do in industry. Whenever you do a new application, where you bring a motor in and you want to couple it up to a pump, the very first thing you do is you put the motor on the stand and you decouple it from the pump. You make sure that they're not coupled. And then you bump it, you energize it for a second, and you see which direction it rotates. If it rotates the way it's supposed to, you couple them together. If it rotates in the wrong direction, what do? You rotate, you grab A and C, and you switch it around. The problem is, darn it, I gotta switch A and C. How do I know which one is A and which one do I know is C? So you can do A and B?
Yeah.
Is that a confident yes? Let's try it.
Station still in the same direction as swapping.
Say that again?
If you, like, it gives you the same magnetic field vector.
The magnitude?
Yeah, should.
But does it give you the same rotation? Remember, originally it was counterclockwise. Does swapping A and B result in clockwise direction? You hope so? Let's check it here. Let's go back to our original one, right? This is going to be 0. This is going to be minus 120. 0 again. And minus 120. All right. Who are my MATLAB pros that can help me straighten this out? Why did I do that? I just keep doing the same thing. I thought I clicked here and who can help me? I'm going to swap B and C now. So I got to go back to here. And what do I do? Yes, ma'am. So I still am going to swap B and C prime because remember what happens is this is coming out of the motor. It actually only, if you connect over here, it actually only connects externally. That's at the motor junction box. So literally on the side of the motor, you actually have 6 leads coming out of the actual casing of the motor, but then you will connect those 3 phases in that location. You just connect them at a common point. So here's B and C prime. And then, oh no, I want to do A and C. Sorry about that. A and B, yep. Okay, so I want A and B. So this is A prime, and C prime don't change. All right, so what's the direction of the magnetic field because of A? Positive current flowing in A. Like that? That's B sub A. How about B? C? Looks awfully similar to the first one. All we've done is swap those two. Okay, so help me out. How do I fix that in here? This is at 0. Everybody agree with Barzilay? Good. All right, so now I'm going to start these both at 0 and run it. Okay, so it's not starting at minus 90 or minus 30 degrees, right? It's starting at minus.
Brought to you by Walmart. Save money, live better.
Hold on. Oh, he fixes stuff, so. Guess I know where he's shopping today. So that would be minus 150 degrees, okay? So now let's rotate 30 degrees. How many people say it's going to rotate in the same direction as A and B, original A and B? Anybody? Who's going to say it rotates in the same direction as a swap of A and C? Any reasons why? You believe that, or you're just hoping? Let's check it out. It's swap direction. So I lied to you. Remember when I said you got to go swap A and C? That was a lie. It was a white lie. I can swap A and B and get the same direction.
B and C.
I could even swap B and C. You want to do that for homework? You do B and C? It should take you less than 5 minutes to do that.
B and C. Would you get the same work of the first time
If I do it from now or from the original?
from the original? You saw B and C.
Oh, somebody says if you swap B and C, will you get the same one as the original ABC? Want to do that for homework?
We just have to copy this.
You already have the code. Didn't I upload this to Brightspace?
Oh, yeah.
Because I remember I was giving Barzilai a hard time because he checks me on everything I do. So I'm like, go ahead and check this. Yeah, I haven't heard you say, hey, is this right or wrong? You haven't done it yet. So no, that's the thing. You can check it if you want, but you can swap any two leads and it reverses direction, which is a beautiful thing. Because again, remember why the whole reason why we like 3-phase and we didn't go to 4, 5, and 6 phases, we didn't have to keep track of the phases, right? They always had the same magnitude and that voltage difference between any two phases was always the same. So isn't this even better? Well, we can connect the motor up and all I have is 3 wires coming in. Do I even care how I connect it? The electrician's just going to be told, hey, wire this motor up and do a bump test. The electrician doesn't care. They'll just land the 3 wires any which way they want. They'll energize the motor and see if it rotates in the right direction. If it doesn't, they'll just swap any 2 leads. So it really is a huge advantage to do this because you don't have to keep track of any of the phases. Makes it incredibly easy. Questions on that?
Since we have A, B, C, we can type them before that. We have.
You can go, you can swap A to B, B to C, and C to A. So you get 3 options, right?
And then AC.
Well, C to A is the same thing as AC, right?
Yeah, the option. So in the 3 options, we have 3 ways of rotating, right?
Rotating what?
So which means we have 1 way which goes clockwise and the 2 other way goes counterclockwise.
No, you can actually get multiple ways to go clockwise. You can do A, B, C, and if we swap all 3 phases, so we had A, B, C here, we could do C, B, A here, and we could also get that. So you get the same number. You have 3 ways to wire it to get it to go in the clockwise direction, or 3 ways to get it to go in the counterclockwise direction. You have exactly the same amount. Avery?
Why are we multiplying like BC and BD by over 2? I know that it's cosine for me, but I will.
Oh, this right here?
Yeah.
So all I'm doing right here is, you see this sign of minus 120? I'm converting that to an actual number. Because the actual current flow through here has sine of omega t. I don't know what that is. So if I plug in omega t equals 0, then I know sine of 0 is 0. That's why you can see this is 0. The sine of minus 120 is a square root of 3 over 2, et cetera, et cetera, et cetera. This is just a way of adding it together, hopefully easier.
That's coming from like the instantaneous value of the current.
The time domain value, yep. In any instant in time, and that's why I said at t equals 0, this is what you get. We also do the same thing at t equals t1, so that you get a positive 30 degrees of current rotation. You end up with this value here. And then the sum is, and we proved it, right? We actually did it in MATLAB. We went from this to this, did we not? Yes, sir.
Just on the last slide, why did the sum angle -30?
For the previous ones?
Yeah, when I asked all those, I got in that one.
Positive 150? I don't know. When we did it over here in MATLAB, I thought, let me take a look and see. We just swapped A and C. So let's see. Let's do these both at 0. I got minus 30 when I added them in MATLAB.
I had my,
Okay. So I got minus 30, which matches what we had here, right? We have minus 30. Then we do it again at minus a positive 30 degrees. And we get minus 60 for the second one, right? Which matches what we have here in the slides. The other interesting thing about this too is from a phasor relationship, right? If we think about the phasors, we have IA, IB, and IC like this, right? Those rotate that way, don't they? They're always rotating in a counterclockwise direction. But I find it interesting that just the way that you connect the phases, you can actually get magnetic field that rotates in the counterclockwise direction. I'm not changing the currents. Remember, the currents are dictated by the power source. It's just that the way I've connected them swaps things around. This is the reason why DC died, because of how simple it is. I just run 3-phase in there and I get a nice rotating magnetic field, and I can get it to rotate in any direction I want. To do that with DC, you needed commutators, you needed to swap power supplies. It was incredibly complex. And if you look at a starter motor, so some of this will get more important to you as you get further into your careers. But here is an actual, is that legible enough? I can't tell. Can you see it? No? Let me do it this way. Guess it doesn't like my plussing. More better?
Yeah.
So you can go buy a starter, which is something, so when you start and stop motors, they have to be started and stopped maybe hundreds of times a day. So you have something called a motor control center with a motor starter, and it basically has contacts. Look at the motor in this direction. You have the motor over here. The overloads normally are part of this. If I wanted to go in the forward direction, I just close those 3 phases on it. Look what I do for the reverse direction. I take A, run that through here, B, run that through here, and C, run that through here. So what have I done? A was originally coming in on T1. Now it comes in on T3. B was originally coming in on T2. Oh, it still comes in on T2. And C, which originally was coming in on T3, now comes in on T1. So even in the real world, that's all they do. This is a motor that can go forward or reverse. Like a crane, you do this all day long. So physically, that's what they're doing in the field. Obviously, you're not going to send an electrician out to swap the wires again. We talked about the example of an elevator, forward and reverse, up or down, right? You just decide which way you want it to go. Okay? Works beautifully.
But then after I think the AC motors for the speed can very complicated content quite much.
Yeah, so what Barzilai is saying is the speed change in AC motors is very difficult, and it depends. So you have a synchronous machine that we'll talk about. That speed is fixed based on the number of poles or the pole pairs. In an induction machine, the speed is variable based on the load. Usually that's not a problem. Sometimes it is, but usually it's not a problem. If you really need to do speed control, so we talk about 60 hertz putting out around 1800 RPM or 3600 RPM. You can actually have a variable frequency drive that instead of 60 hertz, it puts out 40 hertz and you can control the speed that way. So in the past, what people have done is you would buy a motor. So we would buy a motor here and we would connect that to a pump, which runs water out or whatever. And so what would end up happening is you have a recirc line. So in here, you would just recirc the water back in this tank. So if you had too much water control, in the old days, they would just dump water back in. They would design the system that actually would have way more capacity than what you needed and send it back to there. Anybody here drive a car? How does your gas, how much gas do you need for your car? Depends on how much you press the throttle, right? Your fuel pump is designed to just put out a certain amount of flow. So it always puts out more than what was necessary. So then what you do is you have a recirc line that goes back into your fuel tank and dumps the excess fuel. Anybody know anything about furnaces that use diesel? It's home heating oil. Nobody knows that. Anybody have it? Well, on there you have one oil line that goes there. And what happens is it recirculates back into the pump itself. So it'll provide whatever flow rate that the maximum, the worst case scenario, it always provides at least that amount, and then it'll recirc back. So the reason why I use variable frequency drives is designing a system like this costs a lot of money, and it's a waste of energy. I'm pumping more water than I need, and I got to send it back. It doesn't do anything useful. So you can have more efficient designs by using variable frequency drives, and that makes it work. So for 40-volt systems, variable frequency drives have been around for 30, 40 years. And you can actually buy medium voltage variable frequency drives, 4,000 volts or so, that actually you can vary it, but those cost quite a bit and they're more sophisticated. So some people may or may not use them. It just depends on, what the efficiency penalty is you're going to use. But that's what electric cars do. EVs, they use AC motors and they just have a variable frequency output. Take it from the battery, convert it to AC, and run whatever frequency you need to. For braking, you run it at a lower frequency than the motor is running at, and that's how you have regenerative braking. Questions on this? Pretty important concept. It's not like a technically advanced concept, but it's so important to understand how these work, because you really will see in industry, people just expect you to know. You can walk up to an electrician and an electrician knows, hey, I just swapped 2 poles and then I get the rotation that I need. Okay, so now we have the stator part, and that's great, except we just have a rotating field. And for rotation, we actually need another magnetic field. So let's put another magnetic field, and we'll put this on the rotor part. So you see the air gap here, and this one's rotating. And this is the easiest magnetic field that we can create. We can run a set of windings on here and get a current flow through here, which will give us a north and a south. Okay. So remember, we've got a magnetic field here that has a B net over here, and they're trying to chase each other. This gives me a magnetic field on the stator or the rotor, and this is equal to the stator magnetic field, and they're chasing each other. They're just going along and chasing each other. And this one spins a full 360 degrees, right? So the speed of rotation over here is dictated by the fact that I have to rotate a full 360 degrees before I get back to this, this point A, if you will, a magnetic field that results of the current flow from point A. So in this case, we have 360 mechanical rotation and 360 electrical rotation. Okay. The motor has to operate the full rotational speed around as corresponding to the electrical one. Question?
Yeah, how would you get the current into the rotor?
In here,
Yeah,
you use brushes and slip rings. So basically, you run a set of wires over to here that has, some contacting elements, and then you have something that slides along here and makes contact with it.
and then that's the current is DC.
The current would be DC.
Which
It
means
doesn't have to be, but in this simple application, it's DC.
you have to transform from AC to air DC.
Yeah, but that's a rectifier bridge, right? You can buy those for 25 cents or something like that. Going from AC to DC is pretty simple. Going back is a lot harder, but going from AC to DC is pretty easy. You could also, if you don't like this, just get a permanent magnet. You can get a permanent magnet in there and you can do that. Some electric vehicles, that's what they do. You use permanent magnets because I have less current that I need to run. I make the system more efficient. So you could use permanent magnets. How about if we double the number of poles? So you can see now instead of A, I have A2 and A1. And now I've divided that motor in half. Okay? I still have a north and a south over here, but now they're in this direction here. So what I've done, whoops, over here. What I've done is I've basically divided the motor in half. And so now this magnetic field from A2, I see that I have a magnetic field that goes over here. Similarly, I have a magnetic field over here and one over here. So I only have to rotate mechanically 180 degrees from here to here before I restart, when I start doing my magnetic field over again. So when I double the number of poles, I went from 2 to 4. My currents are coming in, right? Those are always at 360 degrees. They're always rotating at whatever the equivalent to 60 hertz is. But this one over here, I only have to rotate half as fast before I go back to another current magnetic field or magnetic field from the currents flowing in the stator windings. So I need less and I need half as much. And that's the way to get a motor that operates at different speeds. I double the number of poles. I went from 2 to 4 and I have the speed. Most motors are 4-pole machines, mainly because of the mechanical systems. It's easy to make mechanical systems that can run around 1800 RPM. It's very difficult, or not very difficult. It's more difficult to make mechanical systems that can run at 3600 RPM. Yes, sir.
Yeah, so you double the pole on the expansion,
And the rotor. I have to double them in both places.
so are they proportional?
Yep, they're always the same. Always the same. So here's where we can come up with our table. So we have P, which is the number of poles. And you notice there's not an odd number to be found because you only ever have an even number of poles, right? You can't have a north without a south and vice versa. And in 50 hertz land, if you're in Europe, those 2-pole machines will run at the equivalent of 3000 RPM. That's the synchronous speed. We'll learn about the difference between mechanical speed and synchronous speed in a little bit. But that magnetic field in a 2-pole machine always spins at 3000 RPM. Either, well, for me, this is counterclockwise. For me, this is clockwise, right? So it always spins at that speed. If it's in 60 hertz land, it runs at 3600 RPM. If I double the number of poles, now I'm at 1500 and 1800. 1000, 1200, 750, 900. So remember we talked about those hydroelectric facilities where they can't have a high speed. You need a lot of poles to get from point A to point B. Yes, sir.
This is a synchronous machine.
No, this is not a synchronous machine. This is synchronous speed. There's a difference between a synchronous machine. What we're talking about over here, this magnetic field, that's the actual speed of the magnetic field. And whether it's a synchronous machine or an asynchronous machine, those magnetic fields always operate at synchronous speed.
But then the mechanical speed same as the magnetic field speed.
Only in synchronous machines. In asynchronous machines, listen to the name, right? It runs asynchronously, so its speed is different. Nope. This is the synchronous speed. It's not a synchronous machine. It's a synchronous speed. So those magnetic fields always run at the speed, regardless if it's an asynchronous machine or a synchronous machine. And just for giggles, I'll show you, I have a very large, well, I don't know what you'd consider very large. What would you consider a very large generator? What size would you consider that to be? Standalone generator, yeah. What would be a big generator for you all? If you walk up, you'd be like, whoa, that's a big generator. Those are physically big, yeah. But if you look inside the Hoover Dam, there's a lot of concrete for the water level, but the generators themselves are actually pretty small. I generally think anything over like 50 to 100 megawatts, I would consider that to be fairly large. How about this one? 307 kVA, 7,000 kVA or 300 MVA. These are located, and I don't know if I put this up here. This could be useless information, but have I put this up here yet? I spent a lot of time here. Not that anybody cares, but okay. This is out in Western Massachusetts. Where's the generating facility in here? There's a solar field here. I think that's 4 megawatts. Where's the generating facility? Right here? What is this? There's a lot of wires and stuff. Shouldn't this be the generator? Yeah, there's no generator in there. There's a bunch of breakers and I think these are these are probably cap banks. There's a transformer here. Oh, sorry, on the other side. Transformer here. This is a control house. So where's the generator? It's on the lake right here.
What type of?
It's a hydroelectric facility. Do you want to go on the river? Okay, where is it? Just see fields here. I don't see any generators. Okay. Here are the power lines. Up or down? This way? You're right. Dylan's right. It's down. It's down in the mountain. This is a 1,200 megawatt generating facility that's underground. It takes water from the Connecticut River. You can see the inlet right here. It pumps it to the top of this mountain here. When it needs to, it's pump storage. So it pumps it when electricity prices are low, and then it drains this reservoir when the power prices are high. You know, it's a little bit weird because, you know, this looks like normal, but if you look way over here, you don't usually see things that are this perfectly, you know, straight and whatnot. But the hydroelectric facility is actually located inside this mountain. Anybody want to get a tour? I don't know if we can get tours. It's a long drive to get there, but it's basically you can have 2 simultaneous soccer matches happening at the same time, looking inside the turbine deck. That's how big it is. So I do have video of it, but let's see if we can look at pictures inside. Oops. Come on. Let's see if I can see some pictures. Here. That's inside the mountain. You can see you got 4 generators. It's hard to see here, but this is the actual mountain. It's actually been drilled out of the mountain. And they actually have fencing here to keep all the rocks and stuff from hitting all the stuff. But you can see there's a bunch of stuff that I don't think that stuff is there anymore. But these right here are the generator circuit breakers. So the generators these are the ones that go to the rotor. Those are located here. The generator is right below it. And then they take the power, go over here, and then they have transformers. The transformers are actually inside the mountain. It's the wildest thing. You're standing next to a transformer and you look up and you see 345 kV high voltage bushings that are inside of a mountain. Usually you wouldn't want that, but these are actually inside the mountain. So why did I talk about that? I didn't want to get sidetracked. Look at how many poles. Get there from here. Well, I missed it. I must have missed that. Here we go. Rotational speed. I'll give you 1 minute. Tell me what the actual number of poles are for this machine. It only spins. Its rated rotational speed is 257.14. So tell me what the actual speed of operation is. 257.14. Anybody want to put their test grade on that? 28? You want to put your test grade on that?
Goes high or down?
What's that?
It goes high. If I pass, my test grade goes high.
No, it's either all or nothing, 100 or 0.
Yeah, I'm pretty very.
Feeling confident?
Just about checking it. It's 120 times. Yeah, right. 120 times. That's what I see, right? Yeah, that's 120 times. You can see it.
I'd love to get a tour of this place, but it's wild. When you go there, you're actually driving into the mountain and you look to the side and there's a pipe, there's a piece of conduit that says 345 kV, do not touch. You're like, I could reach out to my window and touch that. It's a little alarming, but it's all underground. There's no natural light there. What's that? Yeah,
Yeah. so
at 345 kV, they thought it worked so well.
might get it.
Yeah.
Yeah, it's this one.
When I woke up, I had a flat tire this morning, so I don't know, I got some metal or something sticking through it, so I gotta figure that out.
How'd you get in?
I have a bike pump,
It's gonna be flat when you get back out there.
probably, but it's good exercise. Anybody want to go to pump the tire instead of go to the gym? There's about 100 pumps to get it from whatever pressure it was to driving pressure, so.
Might want to put one in the pit there.
Or I can just use my bike pump, and get a little exercise.
Okay, that makes.
What's that?
So that maybe involves it, not like a cigarette by any time, but.
That's too highfalutin for me.
I got 14.
So one person said 14, one said 28. Are you guys betting your test grades on it? Anybody else?
I'll go for it. It'll be fine.
Well, here's the answer. So we're in 60 hertz, right? Because it's in Massachusetts, so it's reasonable to assume it's 60 hertz. So the next question is, we said the mechanical speed and the electrical speed are the same, right? When you have two poles. So I know that my synchronous speed, we'll call it N sub S, has to equal 3,600 when you have two poles, right? Or one pole pair. So if I take the number of poles that I have and divide by 2, won't I get 3,600? So now, if it's 257.14 equals 3,600 and divide by P over 2, what do you get?
That's
What's that? Anybody want to calculate it?
I didn't multiply the denominator by 2 and I got 14. So
Let's see, if I multiply, let me make sure I did this correctly. So I multiply both sides by P over 2. Actually, no, it's the other way around. 7,200, right?
we're doing so.
What's that? 7,200 divided by 257 should be greater than
14. It's 14.
14.
If we use 7,200, 14, it makes sense. Because I did first 38, people double, the number, the time.
Oh,
Why 14? Why is it 72?
Let's do the equation over here, so we'll do it correctly. All right, so we know the equation we just developed is the mechanical or the synchronous speed of the magnetic field is always going to be equal to 3,600 divided by P over 2, right? Because we don't want poles, we want pole pairs. Because if we just divided by P, then it would be 1,800, right? We need to be 3,600 equals 3,600. So NS times P over 2 equals 3,600. NS times P equals 7,200. P equals 7,200 divided by the synchronous speed, which is 7,200 divided by 257.14.
That's 14.
Let's try it. So 7,200 divided by 257.14, 28.
No, times 2.
7,200 is times 2.
Yeah, but then you divide by 2 times.
Nope, there's 28 poles or 14 pole pairs.
Yes, 14 pole pairs. Yeah.
So there are 28 poles
Or 14.
or 14 pole pairs.
So pole pair is like A and A prime? Yeah.
No. A and A prime is the current going in and coming out.
Right.
A pole pair is a magnetic pole, north, south. So a magnetic pole,
Could you pull up like the one that shows the 4 poles?
the windings,
Yeah, yes, like that one.
yeah, so this is a north and a south. That's one pole pair or 2 poles. Remember the net magnetic field, the net magnetic field for the current for phase 1 would have a north and a south as well. Right, if you have a magnetic field, you get a north and a south.
So this is 4 pole pair.
So
Pole.
this is 4 pole. We just use this table to use here.
Okay, and that, okay,
So this is a 28 pole machine. Now you can calculate. So hydroelectric facilities tend to have way more poles. Most reciprocating engines or gas turbines have 2 poles or 4 poles. If you're a reciprocating engine, that's really fancy. Like if you're a low speed diesel, you might be 900 or 1200 RPM, but those are very, very expensive. So if you were to go to Milton Cat or Caterpillar engines and you wanted to buy a 2 megawatt generator, most likely it'll be an 1800 RPM. You can check and see if you want. If we have time after class, we'll do that. So we can do all that stuff with a number of pole pairs. So our speed of operation is based on the number of pole pairs, which means if we want to get our mechanical rotation, we just multiply that by the number of pole pairs. So if we have to go 360 degrees, then we can see that our mechanical operation, we have to have 180. Our mechanical frequency, so again, how fast something operates mechanically. Then we do radian frequency. And if you want to go ahead and calculate what electrical frequency is, really is to determine what the mechanical speed operation is. You take your electrical frequency, multiply it by the speed of operation times P over 120. That was just a more efficient way to get the answer.
You said 180, the angle?
Over here, so 360 electrical degrees in a 4-pole machine corresponds, so I only need to operate 180 mechanical degrees. So I only have to rotate half as much to get 360 full electrical degrees.
Then the frequency is for the F one.
The mechanical frequency, so how fast it only has to rotate at 30 hertz in a 4-pole machine. So each time it gets to the same point, it's 30, it has to happen half as many times as the electrical. And so the idea is your mechanical speed is essentially what you get for a tachometer. People don't even know what those are anymore, but you used to have something for timing that it would flash a light, and depending on how it's speed, you would actually flash it. That's how you check timing. I don't think people know how to do that anymore because does anybody know what a distributor cap and a rotor button is? You can say no. I don't think they've been around for 40 years, but that's how cars used to control ignition. You would just measure rotation now.
Then what is the NM?
NM, this is actual mechanical speed. This is N, which is your speed in RPM. Omega is in radians per second. Yes, so because power equals torque times omega, the more poles you have, the less torque you've got, right? So that's why when you look at that picture for Northfield Mountain, if you were to look at the shaft diameter on these things, these are like 2 feet in diameter because there's a lot of torque. These are really working hard to spin. Whereas if you go look at a 300 megawatt generator that spins at 3,600 RPM, 6 inches, 8 inches, much, much smaller.
Same, more poles equals more torque.
More poles means less torque.
And more. And less speed.
That doesn't most efficient.
Let's do it this way. Power equals torque times omega. If the power output's going to be the same, okay, we'll make it easy. If omega drops because you have more poles, what does torque need to do?
So
Torque goes up. So as I increase, so if omega drops, what has to happen to the number of poles?
That's omega M.
Omega M. What happens to the number of poles? If my speed, my synchronous speed goes down, remember we started at 3,600 RPM, and that was P is equal to 2. What it was 1,800 RPM. So we increase the number of poles to decrease the speed.
Yep.
So the number of poles increasing means we increase the torque. Yes, ma'am.
I would do like a 50cc motor would be.
50 cc.
Yeah.
I don't even know what a 50 cc motor is. You mean the,
Like,
well, that's a reciprocating engine, right? Totally different. Because at reciprocating engines, you could use a turbo, you could use high compression ratios. There's all kinds of different things that have to do that. So normally in motors, we don't rate them in terms of displacement because they're just whatever size they need to be. So normally when you rate a motor, it has a frame size and a horsepower rating and a voltage rating. But it is not really a CC because there's no displacement. I don't know if I'm stating that correctly or not. Yeah, when you go buy an electric motor, you never say I want a 49 cc motor. They would look at you and be like, I don't know what that is.
I'm just really trying to think about what makes me kind of like,
Well, all you need to do is figure out what speed of operation, and what amount of power output do you need. You just have to do it that way, and then you size your motor. That's what a mechanical engineer will tell you too. I've got a pump application that needs 96.7 horsepower under run-out conditions. So what do? Go out and buy a 97.6 horsepower motor? No, you buy a 100 horsepower motor because that's off the shelf. Not exactly, but you can buy 100 horsepower motors. They're all built for you. You'd never buy a 97.6 because they would just be hard to find. So you always oversize it. So the same thing in your application, as long as the speed's not an issue, you can just size it for what you need.
And then also doing the all like gearing it down.
Yeah, exactly. Same concept. But it's interesting because you don't have a transmission, so you're not really gearing anything down. You're just physically fabricating it to do different things.
The formula that we use for the synchronous speed is the same as the last formula that we had, the FE equals to.
Yep. That's exactly right.
Between N and synchronous speed.
We called it NM. This is rotational speed in RPM. So if you had plugged in 257.14 here, and you plugged in 60 here, you should have ended up with 28.
Yeah. Between N and the same as the synchronous speed.
Yep. We'll see why that changes. If you buy or build a synchronous or induction machine, you kind of have 2 rotor types. One is a salient pole, which is basically laminations with these slots kind of available to you. And then you have this round rotor, which is just a big hunk of metal that you mill out where you want the windings to go. So this is all a solid piece of metal. This is all laminations. Normally, this is slower speed. You run those at slower speeds than the round rotors. Oh, the other thing too, as I said, is it's hard to see. This one actually has all the windings removed, but this is where the windings would live. Over here, these you can't even see them. They're all pressed right here into that red slot. You press the windings in there. This picture does a better job. You can actually see the windings going in and being held in here and held in that direction. So this is a high-speed application. This is the round rotor. So normally it's driven by a turbine. Turbines can run at 3,600 RPM really well, They can also run at 1800 RPM, okay. But anything less than that, you start getting into problems. So you'll find these 1800 RPM and less. They're cheap to make and easy to do. But you'll see the magnetic field on a 2-pole machine and north-south. On a 4-pole machine, hard to tell, but you've got the north coming out here and the south returning back. Really quickly, this is important to us in my students in controls. We talked about the concept of back EMF voltage. This is actually how you generate a voltage across the windings. So you have an inductor for your winding. You can represent it. If you provide an AC current over there, that's going to draw as much current as it can until the inductance is canceled out. So what ends up happening is you have to generate a voltage here so that this current through here is decreasing. And this voltage is primarily determined by how much power you're taking out of the machine. And that's determined by this equation over here. You have a machine constant K, you have a flux P, and you have an electrical frequency there. These two can't be changed. 60 hertz. And a machine constant is a machine constant. The only thing that you can change is the flux in the machine. So you can either increase or decrease the amount of flux. One way to do that is when we talked about over here, you actually can put more or less DC energy into these windings. Another thing you can do is if you're trying to pull more power out of the machine or equivalent power, you're running more current into the machine, and that makes it have a higher value of flux. So you can balance the machine just by putting more load on it. So you have to have two magnetic fields, a stator and a rotor. What am I doing on time? We got plenty of time. And those magnetic fields will either fight each other or will help each other pull them along. In most applications, you apply your voltage, your three-phase voltage to the stator field and not the rotor field. Why is that? What's easier to wire up? Those things are fixed, you wire them together, or something here that has to rotate forever. How do you get the power in? It's a lot harder to do, right? You have to have those sliding brushes and slip rings we talked about. So you can do it, it's just a lot harder. So the vast majority of your stator magnetic fields, the net magnetic field you're going to get is because of the AC voltage that exists on those windings. The rotor field, you can use a permanent magnet. Barzilai was talking a little bit about this earlier, is synchronous machine versus an asynchronous machine. Another way to say asynchronous machine is induction machine, and you can induce a magnetic field, which is, again, a huge advantage. Or this one that is supplied externally. In most applications, that's going to be done from DC, but there are some AC stuff that we'll cover. So this is when you rotate. Unless you're using a permanent magnet, you're going to have to use brushes and slip rings to make that work. Can't get there from here without brushes and slip rings. So that's the only thing you can do. And if you have a corded drill, you can go to Home Depot and you can actually see where you can actually buy brushes. They're made of carbon. They have a spring on them, and they wear out over time and you have to replace them. Here's the concept of induced torque. Now we have two magnetic fields, one on the rotor and one on the stator. And the vector addition of those two becomes this net magnetic field. And they're always going to be approximately 30 to 40 degrees or less apart. You can certainly get something that's 90 degrees, but the problem with that is that you're at the limit of stability, and any increase or any change is going to cause you to become out of sync. You're actually going to slip a pole. And so this angle delta is called our torque angle, because that tells you how much torque that machine is providing, either electrical torque or mechanical torque. You can say, hey, wait a minute, where do you get electrical torque from? Well, electrical torque is the equivalent of the induced torque because of current. So you can actually tell if delta is a motor or a generator based on pulling things along. If you see that this BR is first and B net is behind, this indicates that it's a generator. If you swap those two, whoops, and that's a motor. And the way that you increase or decrease the amount of torque is you temporarily slow things down. So if I have something that's spinning at 3,600 RPM, and if I'm driving a motor, I can put more load on it. What happens to that motor for a very brief instant? It slows down a little bit until that torque angle is large enough so that it has enough magnetic pull to pull that along. So if you could look at things in real time, motors and generators do slow down very brief intervals to increase or decrease that torque angle. But then again, they get back up the sync. So these two magnetic fields, very important. BR and BNet always spin at synchronous speed. Doesn't matter what type of motor it is, they're always spinning at synchronous speed. So 3,600 RPM, 1,800 RPM, 1,200 RPM, et cetera, et cetera, et cetera. Okay, on average. That doesn't mean you're going to get a little bit of a torque change and things might blip every once in a while, but for the most part, you want them to spin at the same speed. And that's going to make sure you have constant torque output. You don't want this motor vibrating or this generator vibrating, so you want to keep those torques as constant as possible. And the angle as constant as possible. Yes, sir.
Is the angle from BNet to BR? the other way?
Yep, it's BR to BNet. So if this angle is positive, then it's a motor.
Two.
If it's negative, it's a generator. So if BNet is in front of BR, so BR is your reference.
So in this case, BR will generate.
We have a generator. Yep. And again, that's the nice thing about AC machines. I can build an AC machine that is a motor or a generator. It can do either one. Regenerative braking, right? That's the really advantage of it. So a couple things about power losses. We're almost out of time, and thankfully we're almost done too. All motors, at least in North America, are rated in horsepower. If you go to Europe, they rate them in kilowatts. I don't know why, it's just a different standard. But if you buy a motor in America or North America, it's going to be rated for 100 horsepower. If you buy it in Europe, it's going to be rated for 10 kW or something like that. So here's the thing. Motors are going to be generated in horsepower. That's the amount of output power they can put on the shaft. Again, they don't care about the input power. They only care about output power because our mechanical engineering friends just want to say, I need 97.6 horsepower to drive this load. You need to specify that whatever the system that feeds that motor can handle what the inefficiencies of the motors are. Same thing over here. Your generator is rated in watts. So if you remember from, where is it? Where's my Adobe? I didn't think I had closed Adobe. Thought I kept it open. Oop. So over here, you can see it's running at 307,000 kVA. That's the output capability. It also, because it's a motor, this can run as a motor. It also is a 291,000 horsepower motor. Can run either direction. By the way, this is the biggest motor I've ever seen. That's a lot of horsepower. Anybody's car here can do 200 horsepower? You? I'm impressed. So sports car? Oh, okay. So you're towing something or something like that. So yeah, anything over 200 horsepower is getting to be a fair amount for a car. Maybe you're not for a pickup truck if you're hauling stuff. But if you did 1,000 horsepower, that's pretty impressive. Right? This is 291,000 horsepower. That's a lot bigger than a pickup truck. Try to put this in your pickup truck and see how it goes. So.
That's just for pumping water.
Yeah, so this is interesting, right? Remember, this is a reservoir. So this unit here is at the top of a mountain. So kind of crazy, right? But I don't know if I can see topography map. Let me see if there's a topo map. Let's see. No, there's no topo lines, but in topography, you can get kind of a sense of the height. I think it's probably 500 to 1,000 feet from the top of the mountain. So you take that water and you drain the reservoir to get power out. Well, you got to fill the reservoir back up, don't you? So wouldn't you need just as big of a motor to pump that water back up? Why not use the same motor or the same machine to do both? which is what they do. These units right here, this is the generator part. I mean, this is the field part. This is called the pilot exciter, but right below it is the motor generator. So sometimes it runs as a generator, sometimes it runs as a motor. That's why it's dual rated, 307 MVA or 291,000 horsepower. And that's output. Yes, ma'am. Yeah, so that's what I was gonna say. If you want this to slow down, you can actually either accelerate or decelerate, one of the two. Normally, the only one you have control over is the stator magnetic field. So if you can back that off, maybe make the frequency go less than 60 hertz, like in the car in case of regenerative braking, or you can even flip it around if you want. You can actually get it to spin the opposite direction. But normally speaking, you would never have something that goes forward and reverse at the same time. Like even in the case of an elevator, what happens? You're on the second floor or third floor, the door opens because the elevator stopped. So you never have an immediate transition for going up and down. It actually has this gradual stopping and then it might go down. So here are the different losses, copper, core, mechanical, and stray. Transformer, it's basically a transformer, except we got a couple more. We have mechanical losses because now we have something that's rotating. And then unfortunately, we can't categorize all these losses. So we have something called stray losses. And can you tell if this is a motor or a generator? I say motor, but I make lots of mistakes. Is this a motor or a generator? There's one key thing that'll tell you, well, maybe two, but I say one. Is this a motor or a generator?
Motor.
It's a motor? I have motor or generator, which, anybody want to vote? Who says motor? Who says generator? Do you say motor because it says motor on the slide?
Because I have electricity and mechanical.
Power in is electrical, power out is mechanical. That by definition makes it a motor. It converts electric power to mechanical power. Same thing for a generator, except our input power is mechanical and our output power is electrical. If you also notice too, where we start losing, right? Because we're in an electrical world, so we start dropping wiring losses, right? I squared R losses. Then this power gets converted. This is the power that jumps across the stator to the rotor. So now we have some core losses, and you can see that there's an induced torque. Because with this power going in, it should be balanced by the equivalent induced torque here. Now we've got some electrical losses, a little bit to deal with on the core. Now at this point, everything is converted to mechanical power, and we got some mechanical and stray losses. Opposite direction, we got the stray and mechanical. Now at this point, everything gets converted to electrical power. We've got some core losses. This is converted again from the stator to the rotor, or rotor to the stator, I should say. And we have some I squared R losses, and this is our power. So all of our power is done via magnetic fields, which makes it extremely efficient. So motors can run at pretty high efficiencies, 92%, 93%, which any of our mechanical engineering friends in here? One, would you kill for 92% efficient mechanical system? Yeah, that's phenomenal. Mechanical systems dream for that. Like if you look at a simple cycle gas turbine plant, what's that, 35%? I know that's mechanical to electrical, so that's kind of, not mechanical to electrical, that's chemical to electrical. But the reality of it is that any mechanical system that you can push 60%, you're really happy. In electrical systems, if you are only 60% efficient, you'd be finding a new job. Not fair, us electrical engineers, just not fair, but that's okay. We cheat, right? Because we don't have to deal. The mechanical world is a lot harder to work with than the electrical world. But magnetic fields are what saves us. And it's a good thing too, because if we don't have a magnetic field that travels pretty well through the air, how are we going to jump across here? With electrical energy, that would be arcing all the time. You'd have all kinds of damage. But in magnetics, I mean, it's happening through the air right now. Questions? hopefully, you had thought this class was fun. We did a lot of good stuff today and hopefully pulls in a lot of real world stuff. But hopefully it's starting to pull together a little bit and why three-phase is just so darn important to us. Really, it makes things easy. Any last minute questions since I'm out of time? All right, have a great day and I'll see you all on Thursday. Take care, everyone.